Hi, welcome everybody on today's presentation about timing verification with different trace solutions. My name is Sebastian Ziegler and I'm responsible in the embedded software department here at Vector about the topic measurement and calibration. And this presentation is purely about how to measure runtime with different solutions. Now, I want to introduce a little bit by the topic to say why are runtime issues so hard to find. I want to give you some basics about timing measurement and actually how do you get a hold of these problems. Why are they so hard to find is because in my understanding a runtime issue solves himself in time. That means you have just for a short period an overload, but then afterwards the runtime issue is gone. You maybe recognized it, but you cannot reproduce it. So that's really hard to reproduce runtime issues, especially with sporadic and event-driven systems. And they can depend on multiple things in the system. They can depend on the memory mapping of your software, how the software architecture is shaped in general. IPC mechanisms play a role here, the efficiency of the code, and also compiler settings. So the reasons are various and the problems are not always obvious. So therefore, let's have a look at the agenda. Let's start with general timing measurement techniques. Go on with how do we actually measure the events we want to measure or which I think are desirable to be measured. And then we are going to have a deeper look at different solutions. So how can we, for example, use a RTM module to calculate statistics on our runtime behavior? How can we make a tracing solution? I'll explain what is tracing, but how can we do it software-based? If we want to be more efficient in the sense of the performance introduced by the measurement itself, there are also hardware-based techniques for tracing, which is, for example, a RAM copy mechanism, which I would like to show here, or a pure hardware-based tracing approach. Especially on this pure hardware-based tracing approach, there's also a presentation by Rudi Dienstbeck in this event series on the topic RT, which is the AUTOSAR runtime interface and the successor to RT to measure these events. And later on, I'll show you how do you actually easily integrate these kind of measurement solutions into the MICROSAR stack. So let's start with a simple motivation. We have a timing problem in our system. A lot of software is being deployed. There is an overload situation of approximately, in this case, 99.73%. But the question is, how do we actually find the reason for this? Or if we have so many, such a high amount of CPU load, how do we understand what we can improve? Let's start with one of the simple mechanisms. I think everybody is aware about it. It's to toggle a pin via a DO, direct input output stream. You can connect it to your ECU with an oscilloscope. It can show you we have the measurement starts, it stops. You see actually the timing behavior on the oscilloscope, but this is actually the nice thing. It's the Pro. It's very high available. You have it there. You can play around with it. It's easy to adapt. But the cons when it comes to timing measurement is, in this case, you don't get really an insight into the system. So, for example, if you want to measure multiple tasks, it's a lot of effort. You always need to adopt a lot of measurement points. You don't get details. You just see start, stop, and you don't know why it takes so long in this time. And especially if you want to compare this with a measurement of your colleague, it's very hard to reproduce because there is no fixed set where you place actually this DO trace. Continuing on such DO measurements, you could also calculate statistics out of those start-stop measurements. You could say, well, in average, I consume on a certain code span a certain time with the minimum values and maximum values, and it consumes overall CPU load. So you get more information out of that if you use advanced techniques. This can be done by software tools, which we see later, like the RTM module. You don't have a hardware dependency there, and it's good for monitoring the runtime of the ECU, especially when you want to deploy new software and then you see how your statistics is being changing. The cons, like I said on the DO tracing, so there you don't get details. If you see a maximum value, you don't know why it's a maximum value. And it's very limited if you really want to do a requirement testing. You see, maybe, okay, I was above a border of a maximum value in the requirement, but you don't know in detail which detailed requirement you're observing for. Which brings us to the next topic. This is the scheduling tracing. So currently, if we are really looking for runtime issues and we don't know what's happening on the ECU, this is mainly really the option to go. So if you remember, for example, in an OSEC OS, there are pre-task hook and post-task hook to define the measurement points. And then you can see, okay, the task starts, the task stops. Task starts, task stops. You can maybe also see if something is preempted. So it gives you way much more detail. It provides also a little bit of a software architecture runtime analysis, but you need know-how to do this. It's not always commonly known how to apply this technique, and you of course need to configure it in your OS. So what we are actually aiming for here is, when we do a scheduling measurement, is we want to measure the complete runtime behavior, which results always in the scheduling. So that means we trigger tasks periodically, we execute them event-based. Some runnables in there, they are also triggered on a certain mode, for example, and all these kind of events result in runtime behavior. And if we would apply a scheduling tracing technique, we could see, for example, when a task is being activated, as it is now, when it starts, when it resumes and preempts, when it resumes back to running, and when it terminates. And what you can see here on the left-hand side, this is basically what we understand as a scheduling trace. So we record with the time span which task starts at which point, and as we observe the whole OS, we can see in the end all the tasks. And out of that, we can offline calculate the runtime behavior. So long story short, to me, the important part is not which measurement technique is to use. The important information is where to measure and what to measure. And this is what I'd like to suggest here, to use a scheduling tracing technique in order to understand what is actually the runtime behavior, which makes your measurements reproducible. So for example, let's have a look let's see how the results of such a solution would look like. If you would observe with OSEC pre and post task hook only one task, you see this kind of information. If you use scheduling hooks like in the MICROSAR OS on the OS, you can see all the tasks on all the cores. Then you can already see who preempts whom. If you add also the runtime environment, the RTE, start and stop VFB hooks for runnables, you can also see what is actually executed in the tasks. And this gives you way much more insight. And with a timing analysis tool, you can later on actually see who preempts whom. And you can do your analysis, and then you can see where is the overloaded situation. So the question is just how to measure these scheduling events with a measurement technique. We know now where to measure, but we don't know how to measure. And therefore, as I said, the MICROSAR OS provides these measurement hooks. Of course, there are also the RT hooks, the AUTOSAR runtime instrumentation. I just use this vector proprietary hook mechanism here for the sake of simplicity. RT indicates with a dedicated hook implementation, each scheduling event. Here, the vector OS schedule hook shows you what has happened before the scheduling and after the scheduling. So that means when you want to do reproducible runtime measurements, use this RT or vector scheduling hooks and place your measurement code there. So for example, if you want to use a statistic calculation tool like the RTM, place it in there. If you want to do a software-based tracing, you could use the DLT protocol. If you want to be more performant, you could use a solution like VX1000 with a RAM copy mechanism, meaning we use software and hardware together. And there's also the pure hardware-based tracing approach, which you see later. Let's have a look at the runtime statistics. The RTM module, which creates runtime statistics, basically is a basic software module here in our MICROSAR stack, and it calculates you, as we saw, min, average, max values. And in our understanding, this suits for monitoring, and therefore it's also shaped in order to work during production. So you can use the latest RTM module in production vehicles to monitor your runtime behavior. Monitoring is a little bit different than doing actual problem finding, I would say, but this is the nicety of this module in order to use it in production. The way it would work is you could integrate the RTM with XCP and Canoe during development phase, then XCP would be disabled, and the RTM statistics are being stored non-volatile. That means when the ECU shuts down, you get statistics of your runtime behavior, and with the diagnostic access, you can read it and understand how the ECU and the vehicle performs on the road. If we want to get these details, like the scheduling trace details, we can use a purely software-based trace mechanism if we, for example, don't have an emulation device controller. This would be by AUTOSAR protocol, the DLT, Diagnostic Log and Trace Protocol, which provides this send trace message API in order to forward the scheduling information of our OS into an Ethernet PDU, for example. So the way this solution works is you can work with each production ECU and send the data via the protocol to a timing analysis tool. That means you don't need to invest into a lot of a hardware setup. Quite straightforward in my understanding, but if you add alongside with the OS a lot of other trace points, that means you introduce runtime impact. So for CAN, for example, it would only help to, it's hard to go into a streaming mode. You would rather write into a buffer and then send the buffer afterwards. So there are things to be considered depending on how strong this interface is between the tool and the ECU. Now, if you want to utilize in our software or in our project also hardware capabilities, we can use a solution like the VX1000. That means the VX1000 provides an implementation API for measurement, which is this VX1000 interface event. And you would connect basically the VX1000 with a JTAG or in an AURIX system, a DAP connector to the ECU, and then you don't utilize the bus to send these events. You can use emulation devices, but you can also do it without emulation devices, with production devices, and you are not really limited in the sense of bandwidth. Maybe one thing to add here, the VX1000 is a XCP-based solution, and the nicety of this solution is you could basically combine application internal measurements, which you do with XCP, with scheduling. So that means you can combine two different views or dimensions on the runtime behavior of your ECU. So the VX1000 provides basically an app driver, a driver which copies the data you want to measure into a JTAG accessible address, and from there the VX1000 polls the data. And what you can see here is your way much more performant in the sense of bandwidth than with a bus interface like CAN or FlexRay. And you can also increase the sampling rate, which is important in our use case because scheduling events that can be quite frequent. Now coming to the purely hardware-based tracing approach, which is the AUTOSAR runtime interface. And AUTOSAR has found a way to combine actually hardware trace techniques with the AUTOSAR standard and the AUTOSAR software, which, for example, is this AUTOSAR OS trace variable access. So what we do here is the OS scheduling hook only writes dedicated information into this variable, but then the variable is not processed by software any further. So we just write it into a variable and we use a hardware trace mechanism to observe this variable. And how it works, we'll see here. So some microcontrollers, they are either production or emulation device. Emulation device, they have the capability to support hardware-based tracing by multiplexing instructions on the ECU. That means when the ECU executes an instruction, this instruction is basically copied into the trace stream without adding overhead to the system. It can do a multiplexing of these instructions by two types. One is really a purely instruction trace. That means when you do a branch, you do a jump, it can fetch a timestamp and then it jumps to a different address. And this instruction you can copy. So the ECU copies it automatically. In this case, you create a lot of data, but later on you can see very detailed which assemblies have been executed. For our use case, this does not fit well because we don't get to know the OS decision. We don't get to know if there's a preemption or not. We just see there was a branch, but we don't know why. And that's why we introduced with RT this data trace approach. That means we write the RT OS trace variable in the OS, and this data access, illustrated here on another variable, is being multiplexed and sent off the chip. On a tri-core, this would look like the following. So we have 6 cores, each of them schedules. Each of them writes into a single trace variable because the access is atomic. We don't need spin locks or such. And we only need to observe this variable in order to understand the complete scheduling of all the cores. Because in the tri-core, there are only 3 processor observation blocks. So if you want to do instruction tracing, you would need to decide which cores you want to listen to. In our intent, we want to understand the full system, and that's why we use this RT approach. So now the question is how to integrate all these runtime measurement techniques into your MICROSAR OS project. And that's why we offer on our homepage, free of charge, these timing bundles. So simply go to Vector.com tier tool suite and scroll for timing bundles. This is basically a free of charge solution in order to integrate measurement techniques like with our partner debugger vendors for hardware trace techniques or with the VX1000 in order to integrate the measurement or tracing solution into your MICROSAR ECU project in order to do timing analysis with a timing analysis tool like TI inspection to evaluate those traces. There are also free of charge possibilities or solutions, implementations for Linux, compatibility with LTTNG, the Linux Trace Toolkit Next Generation, Perf, or the QNX Trace Logger in order to also do scheduling on your adaptive project. Now, let's come to a summary. So, generally, in my understanding, it is important to make runtime measurements reproducible. So use the defined measurement points as we provide in the MICROSAR OS. In my understanding, tracing is really for development in order to understand what the ECU is doing. And if you want to also be aware about the runtime of your ECUs in the production, use a monitoring solution, which is, for example, the RTM module. Thank you very much. Thanks for your patience, and then I'm quite happy to hear your questions.